In this lesson, we're going to take a look at Ohm's law, resistance, resistivity, and temperature. So we derived in the lab that we have V is equal to IR, or voltage is equal to current times resistance. Voltage is measured in volts, current is measured in amps, and resistance is measured in ohms. So resistance is actually not a very creative name, but it's pretty descriptive. Resistance refers to resistance to current. Right? So current is the rate of flow of charge. It's measured in amps. It's a coulomb per second. Voltage is, of course, electrical potential difference measured in volts. Resistance is measured in ohms. Okay? And ohms gets this symbol. Okay? So what is resistance? Why does it arise? Well, it's because charge is being pushed by this voltage, and there is basically some internal friction to the conductor, whatever the charge is moving through, that is preventing that from flowing. And we actually give that quality its own name. We call it resistivity. Now, resistivity depends on the material. So what we have is resistance R is equal to resistivity rho times the length of the conductor divided by its cross-sectional area. And if you think about what that means, if I have a long, narrow, thin wire, it's going to have a higher resistance than an equally long wire made of the same material that is bigger. Okay? And essentially, the bigger around our conductor, the more volume, I guess if you think of it like water through a pipe, the more volume of water we can get through the bigger round pipe. But if it's narrow, we get less water through there. Same with current. The bigger the area, the more electrical current we can get through there. Now this thing, that little rho, that stands for resistivity, and it depends on the particular material we're talking about. Copper, silver, gold conductors tend to have fairly low resistivities. Insulators are going to have high resistivities. But the other thing that is perhaps a little bit surprising is resistance doesn't only depend on the material, the length of the conductor, or the area of the conductor. It also depends on temperature. And so we get this temperature dependence of resistivity. And in lab, we looked at this in terms of resistance. Here we'll look at it in terms of resistivity, but it's essentially the same equation, where we have the resistivity at a new temperature is equal to the resistivity of the thing at its original temperature times 1 plus the coefficient, the temperature coefficient of resistivity times the change in temperature. Now, what this allows us to do is calculate how the resistance of something will change when the temperature changes. And we can see if the temperature goes up, our change in temperature is positive, then our resistivity will also go up. So higher temps mean more resistance. And it gets back to what's going on inside a conductor when there's higher temperatures. Higher temperatures means that the particles, the atoms, are moving more. There's more random motion. So instead of all the electrons being streaming in a nice one way, the higher temperature we get, the more random motion there is, and so the harder it is for current to flow. However, there are some things, some semiconductors, that actually have conductors that actually have a negative coefficient. So if A is negative, that means increasing the temperature decreases the resistance. And that actually has to do with the crystal structure of the semiconductor. So only outer electrons, valence electrons, tend to conduct electricity. But when we heat them up, we might knock some of those electrons up into the conduction band and allow more electrons to actually transmit charge. So some things actually can decrease in resistance when they have a negative coefficient or temperature coefficient of resistivity, and that actually means they conduct better when they're warmer.